If you are also looking for professional certified structural engineering services or courses, then don't forget to check link in description of this video.
In this video, we will discuss guidelines for new reinforced concrete structures. Reinforced concrete structures are the most common type of structures constructed all over the world, and approximately billions of cubic meter of concrete is utilized every year in construction of small to medium to large scale structures. The tallest building in the world, that is Burj Khalifa, is also a reinforced concrete building. So let's get started. Starting with good design requirements. Analysis is required for seismic loads. Detail the structure according to the relevant code. In our case, that is ACI 31819 code utilized for this video purpose. Adequate foundations tied together, beam column joints secured, block wall tied to RCC frames, and ignore criticism of over design from the client side if you think the design is appropriate. So the first concept is strong column weak beam concept. Usually we have a weak beam and a strong column to confirm a structure is ductile enough to undergo earthquake, while a strong beam and a weak column is a signature of a weak structure. Reinforced concrete design, the beams must be the weakest links and not the columns. This can be achieved by appropriately sizing the members and providing correct amount of steel reinforcement in them. Below shown are three failure mechanisms. The first failure mechanism is at any cost we should avoid, as the failure of column is brittle and would cause sudden collapse of the structure without giving any warnings to the occupants. While the part B shows that few columns were strong, but then at a point beam was stronger than column and hinge formed in the column and the structure collapsed immediately without giving any warnings or sufficient warnings. While in the part C we have sufficient warnings in the structure and the structure was ductile enough to undergo huge deformations and gave sufficient amount of warnings before complete collapse. So this can be achieved by appropriately sizing of beams and columns, provide adequate steel in the beams and columns. Requirement for the beams. Closer the stirrups, say at 4-inch spacing near beam ends up 2 times at the beam depth. Spacing can be doubled in the middle portion of the beam according to ACI code. Spacing of stirrups is calculated as but not more than d by 4 and 8 times beam bar diameter. The spacing is closer spacing is provided at a 2 times effective depth of the beam in a distance, and then in the center part of the beam the spacing of stirrups as per calculations can be calculated easily utilizing ACI formula, but should not be less than or more than d by 2. The spacing of stirrups as calculated but not more than d by 4 and 8 times beam bar diameter. This is specific seismic requirement, and the location and amount of vertical stirrups in the beam identify the ductility of the beam and the behavior in earthquake. We have to provide laps of the top and bottom bars at mid-span with closely spaced stirrups. If we have laps in the bars, then we have to confine the bars by providing the appropriate reinforcement and shear stirrups in the reinforced concrete beam. Spacing of stirrups should not be more than 150 millimeters, and this is per Indian Standard Code. Lapping prohibited in regions where longitudinal bars can yield in tension. End of stirrups must be bent 135 degrees as shown in the figure for improved performance of beam during seismic activity. It is always preferred to have hooks bent at 135 degrees as you can see in the figure in adjacent stirrups on the alternate stirrups. So as we can see clearly that a straight bar was bent around the longitudinal bars. The end of stirrups are bent at 135 degrees. Such stirrups do not open during strong earthquake shaking. If we do not rotate the stirrups at 135 degrees, there is a chance that the stirrups may open. Requirements for the columns. Similar to beams, there are specific requirements for column, especially in high seismic zone, which we are discussing in the figure. At least larger of capital D h by 6 and 450 millimeters should be this distance at which closed space stirrup should be provided. Capital D is the depth of the column, HC is the height of the column, and 450 millimeters is the distance that should not be exceeding this one. So this is the distance that should be the larger of these three, and in this distance we have to provide the spacing of ties not more than D by 4. Closer ties, let's say 4-inch spacing above and below the beam. More tie spacing in middle portion of the column. In middle portion of the column, if there is no lapse in the bar, then we can provide higher spacing. But if there is lapping of vertical bars, then we have to space the ties not more than D by 2. D is the dimension of the column in this plane and 150 millimeters. And similarly for the bottom criteria is the same as top criteria. Spacing of ties not more than D by 4. D is this distance I mention again, but need not to be less than 75 mm nor more than 100 millimeters. Spacing of ties not more than D by 2, and similarly for the bottom part. Placing lap splice at the mid height with closer ties. This is for a column being used in high seismic region. If it was a moderate seismic column, then we can provide lap splices at the supports. But in high seismic zone, since we have earthquake moments governing, then we have to provide lap splice at the center. Column ties must pass through the joints, and you can see other slides for the details. Closer ties at spacing improve the performance of the structure under strong shaking. Similar criteria for 135-degree rotation of the ties. For the shear reinforcement for column is called ties, while for beams it was called stirrups. Smaller diameter steel bars that are made into closed loops and are placed in regular interval at the full height of the column. Vertical bars are the larger diameter of the steel bars that go through the full height of the structure or the column. This is a tie bent at 135 degrees. End of ties must be bent at 135 degrees to avoid brittle failure of the column. For example, you can see here the tie was opened and this caused the failure of the column. Primarily, there might be multiple reasons. For example, you can see easily that the properly compacted concrete was not utilized. Also, the tie of the column opened, which caused bending of the main bars. Shear failure, large spacing of ties, and lack of 135-degree hook ends in causing brittle failure during 2001 Bhuj earthquake. Provide extra ties, sometimes referred as confinement reinforcement, and you can see that extra links are added to increase strength of the column, and we have to bend these by 180 degrees both around vertical bars. Beam column joints has a special place while designing the earthquake structures. Beam column joints must be designed to resist earthquake forces. Repairing damaged joints is expensive and nearly impossible when the structure is heavily loaded, and therefore the joint's failure must be avoided. Ties hold together concrete in joint, resist shear, reduce cracking and crushing of concrete. At a beam column junction, the ties of the column are continuous while the beam ties are stopped. So this is a common practice. Beam and column joint overlap volume and common to beam and column, but the column ties are continuous. This is an elevation view. The column ties are continuous while beam ties are stopped at the column. Detail for ductile behavior. Ductile behavior of reinforced concrete member is based on the following principle: confinement for heavily loaded sections, ample shear reinforcement, avoidance of anchorage or splice failure. This is a section for a properly detailed column, and this is the elevation. Hoops, this is referred as hoops and this is referred as ties. Hoops confine heavily stressed cross section for the columns, with hoops surrounding the core and supplementary bars restraining longitudinal bar, all which are closely spaced along the member length. Please note that you have to bend the hook at least 180 degree or 135 degree. In this case, this detailing has to be revised. I left it on purpose so that it can be pointed out. For high seismic zone especially, this is a column beam connection example given. We are showing here the importance of the reinforcement at joint. The column ties are continuous, and this is the similar detailing criteria as per ACI 318 code. And similarly, beam column joint for a ground plus 2-story structure. Beam flexure and longitudinal reinforcement also has a specific criteria when designing for earthquake. When designing for earthquake, we have to have lapse in the bar at the center of the span, as the maximum bending moment are occurring at the beam column joint. While for a regular gravitational structure, you can have the lap for the top bar at center while bottom bar at the supports. Beam sections are designed so that flexible, reliable flexure strength is at least equal to the factor design moment, that is phi mn greater than mu. This is the nominal strength of the cross section according to load resistance factor design or LRFD design multiplied by strength reduction factor phi. For beam, this is usually 0.9 if the section is tension controlled greater than applied ultimate loads. This is a factor load. And the equations for ACI are shown on the screen for controlling the area of steel and the minimum requirements. We have to design any section for the positive reinforcement greater than or equals to half of the maximum negative reinforcement at the face of supports, and similarly at any section the positive or negative moment strength should be greater than quarter of mn at either joint. Similarly, there is a mechanical mechanism shown. Reversing beam plastic hinges tend to occur when spans are relatively short and gravitational loads are low. Non-reversing plastic hinges are undesirable, tend to occur for longer spans or heavy gravity loading. Joint shear and anchorage. Once the flexural reinforcement in the beams has been determined, the next step is to check the joint shear in the beam column joints. Joint shear is a critical check and will often govern the size of moment frame columns. In especially seismic design, shear has a very special criteria for making the size of the columns. The frame yielding mechanism determines the forces acting on the beam column and beam column joint. Hoop configuration. Column hoop should be configured with at least 3 hoop or cross tie legs restraining longitudinal bars along each face. A single perimeter hoop without cross ties legally permitted by ACI 318 for small columns, but is discouraged because confinement effectiveness is low. This is a poorly confined column. This is improved confinement, but it is well confined column, and this confinement is calculated by ACI confinement formula for special moment resisting frames. Detailing and constructability issues. The following are some of the issues based on construction experience, both being good and bad. Longitudinal bar compatibility. When the beam and column are the same width, these bars are in the same plane in the beam and column, and they conflict at the joint. For example, you can clearly see if the beam and column are of same sizes, then the longitudinal bar of the column is conflicting with the longitudinal bar of the beam. This requires bending and offsetting one set of the bars, which will increase fabrication cost. Offsetting the bars can also create placement difficulties and result in bar eccentricities. This may affect the ultimate performance of the structure, which is often not considered in design, as it is a very complicated matter. If the beam is at least 4 inches wider or narrower than the column, 2 inches on each side, the bars can be detailed so that they are in different planes and thus do not need to be offsetted. This is a typical example of beam bars conflicting with the column bars, but it is always preferred to offset the beam bars, as column bars should not be affected or changed and should be following the design criteria. Beam column joined with beam corner bars swept to the inside of the column bars. Because the columns, all corner bars are effective in resisting moment, but the beam horizontal spacing of the longitudinal bars does not matter, as beam is primarily resisting the moment in gravitational direction or earthquake direction, but not in the direction of the slab. So it is always safe to move the beam bars in this direction, not to affect the effective depth of the beam bars. Beam and column confinement. The concrete covers on the beam and column may fall off during response to the ground shaking, exposing the stirrup and tie hooks. A 90-degree hook can easily be bent outward from the internal pressure. If this happens, the stirrup or tie will lose its effectiveness. In contrast, a 135-degree hook will remain anchored to the core of the member when concrete spalls. So this is a poor example of concrete tie. For example, if this type of tie is utilized in the structure and you are inspecting a site, then you must point out this to the site engineer that this is a wrong practice and he has to fix the tie and make it 135 degrees bent. Concrete placement. Regardless of the effort to make sure reinforcing bars fit together, reinforcement congestion is higher in beams, columns, and joints than other structural elements such as slabs. To help achieve proper consolidation of reinforced concrete in these congested areas, maximum aggregated size should be limited accordingly. Specifying half-inch maximum aggregate size is common for special moment frames. Sometimes small aggregate will result in lower concrete strength, but other components of the concrete mixture can be adjusted to offset the lost strength. Another key is to well consolidated concrete in congested area having a concrete mixture with high slump. A slump in the range of 7 to 9 inches may be necessary to get the concrete to flow in congested areas. This is a proper example of column cap column cage. Lap splices are not permitted to extend outside the middle half of the column length and should not extend to the length L0 of the column end. With this L0 length we have already discussed what is this. This was the smallest of three criteria which we discussed here in the column slide. These three distances D, h by 6 or 450 millimeter, this is distance L0. So L0 is this distance and lap splices are provided here and the hoop spacing is adjusted according to the design. And similarly for this column, longitudinal column reinforcement is spliced every other floor to reduce the congestion. This is another important aspect for the foundation design, the seismic coefficients and other factors to be considered when we are designing reinforced concrete structures. The interconnection between the footings is provided by providing plinth beams as well as tie beams where the earthquake forces are very high. Similarly, the grade beams are designed to act as horizontal ties between the pile caps or footing and proper dimension that the greatest cross-section diameter shall be equal to or greater than the clear spacing between the connected columns divided by 20, but not need to be greater than 18 inches. Cross ties shall be provided at the spacing not to exceed lesser of one half of the smallest orthogonal cross section dimension or 12 inches. This is referred for grade beam design base shear. The base shear is the vertical horizontal reaction of the earthquake on the structure and is the total design lateral force or shear at the base of the structure. Total design base shear in the given direction shall be determined from following formula if you are using UBC 97. The total design base shear depends upon the code whichever you are using. For example, ASC 710, Eurocode, British code. But for example, in our explanation, we are utilizing UBC 97. So the following limitations on the formulation are governing. This is the time period calculation for the structure using UBC 97. These are the type of structural system for resisting lateral forces: bearing wall system, building frame system, moment resisting system, dual system, cantilevered column system, shear wall frame interaction, and others. Each of these have a ductility and strength reduction factor for resisting the earthquake forces as well as calculating the seismic forces. Then we have seismic coefficient Ca, seismic coefficient Cv, and near source factor to calculate base shear as per the code requirements. These are the gravitational live load according to the ASC 710 or UBC 97 code. These are the given according to the occupancy of the structure, while the dead loads are simply calculated by density of the material utilized multiplied by the dimensions of the structural or non-structural components such as finishes, partition walls, etc. Soil profile types: SA, SB, SC. SA is hard rock soil profile type and SF is the weakest soil. This is the typical detailing as per ACI code, which we have already discussed in detail. Column strip, middle strip is part of flat slab which we are providing if we have a flat slab system or a two-way slab. Beams in flexure and beams in shear reinforcement details are also shown here as per ACI 318 code. And this is zone 3 and 4 detailing. Zone 3 and 4 is high seismic zone and the labs are provided at the center of the column height, but in low seismic zone the labs are provided at the support of the column. Similarly, here you can see the extra reinforcement are provided here, but we have to provide extra reinforcement for gravitational load usually, so the detailing for extra reinforcement is same. So that is overall discussion for the reinforced concrete design according to ACI code and the basic criteria which you have to understand. Whatever code you are using, the basic criteria is usually conceptually similar no matter how much differences in formulation, but the basic criteria is more or less similar. As if earthquake is coming and the structure does not know what code to follow, it will follow the way you have designed it to resist the earthquake. Thank you for watching. Please hit the like and subscribe to the channel. Bye bye.